development of the real numbers. So, what kind of equation is that?
Qubit.
It's a qubit. It's a polynomial. It's a qubit. How many solutions therefore have we going to have? Three. This part is simply a real number. If k is a real number, I also know that k to the power of 6 would be positive or negative. Positive, because anything raised to an even power is always going to be positive. Therefore, negative 8 times a positive number is going to be negative, isn't it? Why am I concentrating on that? Because I need to look at this and write this in what form? Polar form. Therefore, I need a modulus, an argument. So, let's go to Lord Argan's diagram. No, it was Lord Argan, didn't you? No, right, it's okay. Negative 8k to the power of 6 on our real axis. That's where negative 8k to the power of 6 would have to be, isn't it? Yeah. Therefore, what's the modulus? What's that distance?
8.
Not 8.
8k to the power of 6.
8k to the power of 6. That's the distance. Whatever that happens to be. And what else do we know? Argument must be pi. Another very typical kind of question where you're not working with just a number here, you're working with some other variable as well. But you should still be able to plot the information on an Argan diagram to help get this in polar form. Okay, so let's write it in polar form. Okay, Tyrone, what would it be in polar form?
8k to the power of 6.
Yep.
6.
Alright, good. Okay, if we're going to solve this, two possible methods. I'm going to use the algebraic approach. Okay. Alternatively, you could look for the three solutions, which are evenly spaced around an Argan diagram. Perhaps we'll look at that in a minute, but let's use the algebraic approach here for now. Okay, if I'm going to use the algebraic approach, eventually I want to get rid of that cube. So I'm going to take the cube root, right? Now before we do that, what do? Do something to this. Right, I'm going to add 2k pi. Is that a good idea?
Yep.
No, it's not. Because I've already got k there.
2 in.
And there are two k's, two different k's, meaning two different things.
Change it.
Two
In.
Right. Use some other symbol. Commonly N, standing for number. Okay, so use some other symbol other than K in this situation. Otherwise you're going to get mixed up as to saying, okay, well, are they the same thing? No, they're not. Okay, K here was simply taking the place of what?
A real number.
No.
Oh, that one.
This one. Standing for an integer. Okay, because we're going to put different integers in this, right? Okay, whereas this is simply a real number. This is an integer over here. This is a real number. Okay, so they're not the same thing. Okay, what do we do now? Substitute.
No, you gotta take the cube root.
Root. So all of that to the power of 1/3. And then we're going to do what? Come on, guys. Sounds like, you know,
8 divided by 3.
Friday was 72 years ago, according to your feedback I'm getting here.
You'd find the cubed root of 8k to the power 6,
Yeah.
and you would divide pi plus 2 or in pi over by 3.
So you're using what theorem?
More than one.
The Void phrase theorem. Okay, we've got to apply that. So According to De Moivre's theorem, it would be 8k to the power of 6, the cube root of that. Okay, so what is the cube root of 8k to the power of 6? This is where we need to know the simple algebra indice stuff. Should be simple. What is the cube root of 8? 2. Because 2 times 2 times 2 is 8. What is k to the power of 6 to the power of a third? K to the power of 2. 2. How do you simplify that? What do you do with the indices? Multiply them, giving 2. Guys, if that, if you're not secure on that, if that's something going, oh, I think it's a 3, or maybe it's a 2, well, it's one of those two, but who knows, then for goodness sake, do some revision about it. Okay, go back to, I don't know, look it up. Google it, laws of indices. Look at that first handout I gave you at the start of this year. We did a practice on indices. Why? Because this stuff's important. And they're the basic foundations of it. Okay, so coming back to this, 2k squared. Okay, what do we do with the pi plus 2 in pi again? Sam told us, what did he tell us? Divide by 3. Why? We actually need to do what with these two? Multiply them. But multiplying by a third is the same as dividing by 3. Okay, now what? Right, you substitute n being, because there are how many solutions again? 3. We're going to substitute the easiest value for n, which would be 0, and then 1 and 2. Okay, so let's call this Z1, our first solution. What happens to 2k squared here? That becomes 0 because of substituting 0?
Stays the same.
Stays the same. Does the modulus change in the 3 solutions? No. The thing which changes is the argument. Okay, so if we make n 0, this becomes on top just pi over 3. Therefore, that's our first solution. Let's make n equal to 1. So, z squared. Jason, what would you get if you made n equal to 1, sorry. You make n 1 there. What would you get on top? 3 pi. 3 pi divided by 3. Alright, 2k squared, and Vince, what would you get if you made n equal to 2? You get, I made n2. What do you get on the top?
6 by 1
Look again. I think you said 6.
Yeah.
I don't think you're going to get 6. Make n2.
Oh, 4.
So 4 plus 1 pi?
Oh, 4 pi.
4 pi plus 1 pi?
4 pi, 4 pi squared.
Okay, you're adding 4 pi and 1 pi?
4 pi. 4 plus 1. 4 plus 1. Oh, 5 pi.
Okay. Yes, because 4 pi's plus another pi does not make a square
Yeah,
pi.
5 pi.
5 pi over 3. Okay, 5 pi over 3. Right, there are 3 solutions. Guys, I did mention before, you can use that algebraic approach. Alternatively, once again coming back to this important idea, because you could have done this. You could have said, right, these 3 solutions are going to be evenly spaced around the Argand diagram. So if you went back to this point here and took the cube root of this and applied De Moivre's theorem, you would have got this solution, isn't it?
Yeah.
So if I roughly sketch that, that's 60 degrees, 30 degrees about there. So let's call that Z, we'll call that Z1, because it is Z1. Okay, now if you look at the other solutions, 2k squared cis pi, assuming that distance is 2k squared. That would be there. 30 degrees. And then if you looked at this solution, well, you could go 5 pi around here, or negative 1 pi this way. You end up with, that's not brilliantly drawn, to make that a little more obvious. C1, C2, C3. Should be the same distance. This is our first solution, so this is pi over 3 here. Pi all the way around there and 5 pi around there. The angle between the three solutions is the same. So if you said, all right, I'm going to have three solutions which are 2 pi over 3 radians between them. That angle there, 2 pi over 3, isn't it? So if you started from that one and said, all right, I'll add 2 pi over 3 to the argument. Well, I get this one. Then if I add 2 pi over 3 again, I get to this one. So it's an alternative way you could have got the three solutions. That or that. That makes sense, that I'm talking about here. Okay. All right. Well, that was those three questions. Is there anything still on C or B or A that you wanted to check on? Okay. All right, guys. We'll come back to some further questions in that paper. All right, guys, let's have a look at the last part of this complex numbers work, which is something on the board there, on the whiteboard, called, what's the heading at the top? Loci in the complex plane. Okay, no, it's not Loki, which is a Norse god. Just happens to have a similar name.
My guy Loki.
Doesn't have anything to do with them. Okay, what does LOCI stand for? What does it mean? Who's heard of that term before? Nobody. Okay. This is a mathematical term meaning a set of points which fits certain conditions. You ever heard of Loci before? Okay. Okay, let's take a simple example. Let's say you're asked to sketch a set of points which are all 3 centimetres from A. Well, here's the condition. Set of points, here's the condition. They have to be exactly 3 centimetres from A. Can you talk to the people next to you and discuss what you think that might look like? What the set of points be that are 3 centimetres from A? You're allowed to discuss, so when I say talk, it means you can actually talk. Okay? Talk to the people next to you. How about sketching a few? Okay, what would it look like?
That's very broad. Very broad.
Look right?
No.
That look right?
No.
No?
No.
it there, 3 centimetres from A.
What about the?
But this one's not.
No.
Ah, damn. Okay. Oh, it's there. Okay. Shouldn't have been a maths thing. Okay. Oh, got 4 points. What about any more?
Do some more.
Do some more. How?
Good turn.
Diagonal on a 60-degree angle. Oh, 60-degree angle. So I've got to go 3 centimetres that way.
Yep.
Okay. I'll go back this way as well.
Yeah.
Yeah.
Okay. Now what?
And then flip it the other way.
Oh, reflect it. Right there. Any more?
30 degrees.
Oh, 50 degrees. Okay. 45? No, it's actually 45 about there. 40. That's starting to look like a what?
Circle.
Circle.
Square.
Okay, so yes, a circle would fit that criteria. Okay? And in fact, I'll leave it dashed for a moment. What happens if I said, sketch the set of points less than 3 centimetres from A? What would that look like?
Going in.
Shaded in? Would it be the points inside the circle?
Yep.
Would it be the points on the circumference?
No.
No. Okay, so in fact, if we were asked to do that, we would draw a circle, otherwise I can't shade anything in accurately. But we would draw the circumference like I've got it there dashed. And then we would shade in clearly enough to make it clear we're talking about the points inside. So if I said sketch the set of points less than and equal to 3 centimetres from A, what would we include now? The circle, so we'd have to draw that solid. Okay, so there's a difference between the dashed circumference there and a solid line. What if I said sketch the set of points more than 3 centimetres? I'll draw that. What would be the set of points more than 3 centimetres from A? More than and equal to.
The whole page.
So I just have to keep on sketching forever?
Yep.
No, you just draw
Enough to indicate you are talking about the outside. Okay, so the green area would fit that. And you sketch enough to make it clear you're talking about everything, but not obviously being ridiculous and sitting there forever sketching. Okay, all right. So coming back to this point, the loci definition then, set of points that fulfill a condition. Now, we're going to have a look at this in the context of complex numbers. Circles are going to come up quite a bit in some of the answers here. Another very typical situation would be this one. Let's have a look at the set conditions. What would the set of points which are the same distance from A and B look like? Once again, sketch it and check with your neighbour.
What's the distance?
Sketch the set of points, the same distance from points A and B.
Venn diagram? Surely you've been diagram. It's two circles.
And just try and put them all the same horizontal.
Unless it's just unless it's just touching. Unless it's just touching. Like two circles like
Okay, any suggestions or thoughts?
It could be that or it could be Venn diagram.
Right in the middle?
Line down the middle.
Line down the middle. So, would that point be roughly what? Okay, so you reckon line down the middle. Okay, which way?
Vertical.
Vertical. You mean like this? Why would that be true?
At every point, it's the same distance.
That distance isn't the same as that distance?
Parallel.
Oh, you mean they've got to go to the same place? Okay. You mean those distances are the same?
Yes.
Ah. Okay, so if we took any point on that line and drew a straight line back to points A and B, yes, they would be the same distances. The dashes there indicate the same length. Okay, so any point vertically there, okay, so that point which is halfway between, okay, what's the proper term for, if I draw a line joining those, that's obviously the, what point? The midpoint.